Hello, everybody. Great to see you all. Glad you can join us. See a lot of repeat visitors, which is great to see. So welcome to you. And if you're new here, welcome as well. Please feel free to say hi in the chat. Good to see everyone. How's everybody doing? Any special updates? Any good news from some of our learners? There's definitely some disappointing news that the groundhog saw its shadow. I agree. In Pennsylvania, it hasn't been above freezing in the entire year thus far, so that's been fun. Well, I'm glad to see, one of the things I will say, I'm glad to see that something has already happened in our YouTube chat very quickly, which has really been the case for my entire life, which is that my mom has become more popular than me very quickly. This was always the case when I was in school, all the way through college. It was like, Phillip, when's your mom going to come? And she'll bring some really good food. We like her better. And that happened very quickly already in the YouTube chat. But there's one important rule you should know, which is that she and I have an agreement. And that agreement is every time she tells a story about my childhood, she has to pay me $5. And there's a kicker to it, which is that every time I'm a baby in the story, it gets multiplied to $20. And you might think that that's mean, but the mean thing is that she's never really paid out any of these bounties, even though she has violated the rule many, many times. And I want to start by saying that any of these types of stories that make their way into the YouTube chat accumulate a 10x multiplier. So she needs to make sure that she knows, unlike the Pittsburgh Rivers these days, she's on thin ice with these sorts of things in the chat. All right. Now, our goal today is to get started working on simulating an election from polling data. And how this is going to work is that, just like with simulating the weather, these sorts of simulations work by generating a huge number of trials. And in each case, after we generate a trial, we add just a little bit of randomness. So we add just a little bit of random push to whatever system we're going to simulate. And that simulates real life because we don't have certainty over the future. And then when we add all that little bit of randomness, and we do this, 10,000, 100,000, a million plus times over all these trials, then we see what happens. So what's the average case behavior, or over all of those different trials, what are the probabilities that each of the indicated events that we want to study actually occurs? So that means that in order to do this, what we need to do is we need to add randomness to our algorithms. So we need to learn how to program and in such a way that we can add some aspect of randomness. Now, if you did our reading to prepare that accompanies what we're going to do here, then you already know how fraught this is. It might seem like a relatively simple task, but it's one that historically has a lot of peril associated with it. And we can take for granted the fact that modern programming languages include automatically the ability to generate, for example, a random number between 0 and 1. So if you haven't had a chance to do that reading, feel free to do so. And we have a lot more historical context for this so that you will appreciate that a lot is going on behind the scenes whenever I just call a function to generate a random number for us. In the meantime, we're going to see how all of that stuff works. So our goal is, for now, is to show you what functions you might use to actually generate a number that is at least seemingly, even though it actually isn't truly random, how do we generate a number that seems random to us? And the nice thing about that is, I know I've seen folks say what we've done when we finished the preceding chapter started to get quite challenging. And the nice thing about the course is, I know I've said that everything here is a treadmill, but that doesn't mean that it necessarily is always getting steadily faster. So here is an opportunity, and kind of at the start of every chapter, what we have is an opportunity to step back and do something that is going to feel a little bit more straightforward. It might be new, but the examples that we're going to see that are going to give us this tool that we need, which in this case is random number generation, are going to be based on some pretty straightforward fundamentals. So then we'll, of course, push farther and harder as we go. So I think we're about ready to get started. And in the meantime, as always, whether you're new here or a repeat guest, make use of all our resources, join us on the Discord, and most importantly, make sure to like and subscribe. So like this video. If you're not subscribed to us already, please make sure to do so on YouTube. I think it's time to get started though. Please feel free to let me know if you have any questions in the chat. And the other thing I would say is we won't have a very long stream tonight, and I think that's a good thing. So I know we have a soft deadline coming up, which is not strictly enforced, but it's sort of, if you're following us more or less synchronously, it's an opportunity for you to stay connected to sort of our cohort. And that's coming up at midnight Eastern as of us recording this stream. And so we'll have a special office hour that we're going to have right after the stream stops. So I didn't want to have a ton of content for what we're going to do today. And that's going to allow you to come to office hours if you are a PhiloMath subscriber. So feel free to come over for that. If you have any questions about finishing up exercises, I'll be there for the start of it. So that'll be over on our member voice channel on our Discord. Good luck in getting your assignment finished. We've got plenty more to do, and we've got plenty of problems when we hit the second part of the course and we start talking about object-oriented programming, and we really can go deep into some of the really neat scientific simulations that we're going to make, although everything that we do is cool. And so I think we're ready to begin. So to get started, I have a little bit of starter code here for us in a dice folder, and I have a main.py within my dice folder. And I've got the rules of craps here because we're going to simulate the game craps, but we don't have to worry about that just yet. What I would like to do is to first explain what are the functions that we might use if we're going to be generating random numbers. And there are two main functions that for now, there are a few other ones that you might use, but for now, you only really need to know two primary functions in Python for generating these random numbers. So the first one is, and I'll just put these in comments, we have a function called random.range. It takes two integers a and b, and it generates a pseudo-random number between a and b minus 1 inclusively. So fortunately, this is consistent with what we've seen when we index substrings and when we index sublists, is that, as well as when we do ranging, which is that we include the first integer, but we don't include the second integer. So I've also called this function random.randrange, and one thing I should say is that we're going to import the random package, which is built into Python, at the top of my code. The other function we're going to need is a function that will generate a uniform float in the interval 0 to 1. I think technically it's like this, like it could actually generate 0, but it's not ever going to generate 1. And I should say it's pseudo-random uniform float. So we could probably call these functions. And one thing I might do is, why don't we print the result of calling random.randRange of 0 and 10. So this is going to generate us a number between 0 and 9 inclusively, so 0 up to but not including 10. And then I'm also going to generate a random number between 0 and 1. And I'll do this gives me a quick opportunity to run our code. So I'll save my code, and then let's bring up a terminal. If I can drag the bottom ribbon here. Okay. So I will say, let's navigate into the dice folder. And then what I'm going to do is run my code with Python on a Windows machine or Python 3 on a Mac, and then main.py. So what we see is we generate a random number between 0 and 9. Then we generate a random number between 0 and 1. Feel free to let me know what is it that you generated. So we'll see. We each probably generated something presumably pretty different. So what did you get for these two function calls if you ran it? Great. So what we're seeing is on your computer, you probably didn't get these two numbers. You might have gotten 0. Be highly unlikely you would have gotten this exact same float between 0 and 1. I could do the same sort of simulation though, right? So I could run my own code a bunch of times. I could keep hitting up and enter, and this will run my Python code multiple times. Now, it's interestingly enough, I actually got a 5 3 times in a row. So for whatever reason, I continue to get a 5. But I got 4 5s in a row just for whatever reason. And then now I've finally got a 9. And I can run this like 10 times. And you'll see every time I run it, I'm obtaining a different integer and I'm obtaining a different float. Not necessarily always different, but at least one that is seemingly random. Now, in the early days of Python, when I run this code, I could run it 10 times, and actually, it would always give me the same output. So I wouldn't see all these differing outputs every time I run the code. For a long time, though, we would see the behavior that we just saw. And you might wonder, what on earth would be going on that I would be generating these random numbers and then I actually would have obtained the same end results? So let me show you what I mean. If you did our preparatory reading that accompanies this, you'll know that every random number generator has to be initialized using some value that's called the seed of this random number generator. And so I could actually have access to the seed on Python, which would say, let's say, for example, I want to start the random number generating process by establishing that I want a seed value equal to 0. So I can call random.seed of 0. And when I do that, this is going to establish the start of the number generation process. So this time when I save it, and I run it several times, the question is, what are we going to see? And I'll run it once, and this time I'll ask you the same question. If you add random.seed before these function calls, what does your code generate? So everybody's saying 6 and 0.75795, etc. Everybody's getting the same thing. So it doesn't matter if we're on Windows or Mac or whatever. You're also getting these two numbers when you run it. A couple people also have noticed, which is good, if I run this multiple times on the same machine, I get the same output. And so what we're learning here is that this process is not random. So when we say, think that we are working with random number generation, it is pseudo-random instead. Meaning that from our perspective, when we see a sequence of integers get generated, it appears to be random. It has the properties that a random sequence would have. You see, like if I'm generating numbers between 0 and 10, or it goes up to 9, the likelihood of generating each of these numbers is 1 out of 10. And it's possible that I could get repeated numbers. So I'm not going to have any special rules over not allowing myself to repeat. But when I look at the sequence, it does seem truly random. However, what this shows us is that we can actually force the random number generation process to not be random. And so, for example, if I were to call this function, and I were to call it, I could do this with a for loop, but I call it 5 times. What you're going to see is, here's a sequence of 5 numbers between 0 and 1 that get printed. And when I run the code again, I get the same sequence of 5 numbers. So I can run this a million times. The sequence of numbers is going to seem random, and yet it's anything but random. So this is how Python used to work, and that's how a lot of languages when they got started worked, which is that even though you think that you're getting a random sequence of numbers, behind the scenes, there is a function being called, which in the early days of Python was random.seed of 0, and it would automatically get called for you. And then as a result of that, the sequence that you would get would always be the same. So if you ran your function many times, you ran your code many times, you'd wind up with the same sequence of numbers that's generated. And that's because the process that's going on behind the scenes isn't actually random. It's based off of a controlled process. So my question for you is, if that's the case, then why is it that you think, like, if I don't call this, what do you think Python is doing behind the scenes so that now when I run it multiple times, I don't get the same sequence of numbers? And we saw that before. What is it doing instead, do you think? Claudia says maybe the seed generation itself is random. All right, that's a good idea. But notice the chicken and the egg catch-22 that you just introduced. In order for me to generate a sequence of random integers, I want a random start. So you're right that if I have a truly random start, that's going to allow me to generate a sequence of integers that seem random. Yeah, a few other people have said one of the things we could do is just look at the current time. So one of the things that we might do is instead of random.seed of 0, maybe we could seed this thing based off of the current time in nanoseconds. So I need to import the time package in order to do that. And I'm simply calling the current time in nanoseconds, where I've counted the number of nanoseconds that has happened since some critical point in the past. It's going to be a lot of nanoseconds. But in the meantime, when I run this, what have I done? The only supported seed types are, maybe I need to convert it to an int. Let's see. I thought this would work. Int argument must be a string. Oh dear. Let's see. We are indeed initializing with time. I just want to be able to show you my demo. I think I just forgot that this is a function. Let's try this again. All right, now it works. And now I'm going to show you what I was trying to show you, which is when I run this again, I'm going to get a different outcome. Even though I'm still seeding the random number generator, a lot of nanoseconds are going to pass between the time at which I do this and then the time at which I do this. That's like an eternity in nanoseconds. So as a result, when I pass whatever that integer number of nanoseconds is into the seed, the likelihood, and I think there's going to be some process where it continues cycling, and the likelihood that it will cycle back and hit the same number that it started at before is functionally random. Like, it could happen, but it's essentially going to ensure that for most of the time, you're almost certainly going to get a different seed. The nice thing is that this happens behind the scenes automatically. So when you run Python, it just assumes that this is what you want. And if for some reason you might want to establish random.seed of a specific number, well, then you're going to get a specific known sequence of numbers that you can predict. And that honestly can be sometimes useful if you're trying to test a function, for example, and knowing the sequence of integers that you're going to generate or the sequence of numbers that you're going to generate might allow you to test that function a little bit better. That's why you might want to have random.seed and give it a specific number. And there's a lot to this. So if you want something that is truly secure, then a lot of times what is included with built-in packages in languages is not quite going to satisfy exactly what you might want. There were some cool stories from a few years ago of some hackers, for example, who were able to exploit the random number generation in certain slot machines that hadn't been updated to the most completely secure, up-to-date pseudo-random number generation. And so the patterns weren't quite random, and they were able to use fast photography and stuff like that in order to predict what the sequence of numbers was going to be. But for now, while we're in this realm of casinos, that's going to kind of motivate what we do with the rest of this code along. And why don't we write a function then to roll a single die? So a single six-sided fair die. This function is not going to take anything as inputs. So this function is going to simulate the rolling of a single die. So in terms of parameters, we're going to say, I don't need any parameters in order to do that. So we'll say none. But the return, and now I can say it needs to be an integer. And I specifically know something about that integer, which is that it needs to be a pseudo-random integer between 1 and 6 inclusively. This is actually a really short function, because if I want a number between 1 and 6, here is where I can simply return random.randrange of 1 to 7. So we know that 7 is not included there. And this will give me a random number between 1 and 6. And we're good to go. I can call this function. So I can save this. And I don't know, let's do it 10 times. So I don't really care about the variable that I'm going to use. That's not going to be important. So I'm going to say for underscore in range of 10. And let's roll the die. So I'm going to call roll die. And when I save that and I run it, I thought I had saved it and run it. I don't get any dice rolls. Okay, maybe I need I here. Did I not return it? I thought I did. I did here. Return random.randrange of 1, 7. All right. It's been a long week. What am I missing? I call roll die. Oh, I didn't do anything with it. Got to print it, okay? Oh, even middling coders make simple mistakes sometimes. Okay, that was just a test for the chat, but you all passed. All right. Now we see here's our simulated dice rolls, and I'll say, let's give it just a little bit of more information. So we generate a 5 and a 6 and a 6 and a 5 and a 2 and a 1 and a 2 and so forth. And we could run this a million times, and if we really want to be precise, we want to make sure, like, I don't know, it's never generating a number outside of the range 1 to 6. And if we look at the number of occurrences of 1, 2, 3, 4, and 5, and 6, probably they should occur about equally. So we could test that. I'm not going to do it because that's unbelievably boring. We have an autograder to do that for you. In the meantime, I want to do something which is going to move us towards being able to simulate a game, which is, why don't we simulate the process of rolling? If I can roll 1 die, why don't I simulate the process of rolling 2 dice? So we're going to have a function here then that's going to roll 2 dice. And it's still not going to take anything. It's still going to return an integer. I guess I could return 2 different numbers corresponding to the values of the dice, but I'm interested, for the game that we're going to simulate, I'm interested in the sum of the dice. And we're going to have very similar type of doc string. What's nice about this is that I don't need any error checking either, because I'm not taking any parameters. And in this case, I'll say we're going to simulate 2 dice. And it's a pseudo-random integer between, I guess, 2 and 12. And it corresponds to simulating the roll of 2 dice and returning their sum. Okay. And as we've seen a lot, there are a couple ways of getting at this. So way number 1 is the math way. And the math way is to say, all right, well, what are all my different outcomes? And I have a little dice table here that I can show you. So here are all 36 possible outcomes when we roll 2 dice. So I could have, you might think of this as whatever the first die is showing. This is whatever the second die is showing. And then I could say, all right, well, if the first die is showing a 1 and the second one is showing a 1, then I get a sum of 2. If this first die shows a 3 and the second one shows a 4, then I get a sum equal to 7. You have 36 total outcomes here. Each one of those outcomes is equally likely. And so how we could write this algorithm would be to say, well, let me go through and identify what is the number of occurrences of each sum. So 2 only occurs once, so it'd be 1 out of 36. 3 occurs twice, so it's 2 out of 36. 4 occurs 3 times, so it's 3 times out of 36, and so forth. The most likely outcome is 7, which occurs 6 out of 36 times. And then we have 8 as 5 out of 36, 9 as 4 out of 36, and so forth, back down to 12, only occurring 1 out of 36 occurrences. And that's great. And I could use that idea, now that I've done a little bit of math, to say, if I want to simulate this process, what we could do would be to say, let's make a big if-else statement. Or I suppose this is an opportunity for us to use something that we've seen that might work in another context, like a dictionary, like a match statement. Any of those things is going to work. And so what I'm going to do is instead say, we're going to generate a random number. So this is between 0 and 1. This gives us a float. And it's weird, maybe a little weird to call it roll, but I'm thinking of it as a number that's simulating the process of rolling the die. And then anytime you have a collection of things that you want to simulate, and they all have a bunch of probabilities, and those probabilities sum to 1, there is a classic approach that you can use in order to take pseudo-random number generation and simulate that process. If we go back to our dice table, what I said is that 2 occurs 1 out of 36 times, 3 occurs 2 out of 36 times, 4 occurs 3 out of 36 times, and so on. If you add up all those probabilities, you get 1. So what I could do is I could divide my interval between 0 and 1 into a bunch of subintervals. And then when a random number gets chosen, it's almost like it falls into a bucket. Then I say, which of those subinterval buckets did it fall into? And that's the one that I want to say corresponds to the event. So in this particular case, if I grab my random number and it's between 0 and 1 out of 36, well, my subinterval has length 1 out of 36. So if roll happened to be less than 1.0 divided by 36.0, then I want to return 2. So if it's less than this number, I know it's greater than 0. So it has to fall in the interval 0 to 136. Okay. And then I say, well, let's do an else if. And in the else if, I know that it's greater than 1 out of 36. So if I know then that it's less than 3 out of 36, then this corresponds to the interval 1 out of 36, 3 out of 36. And if that's the case, I can return 3. So that gives me a likelihood of 2 out of 36. That's the width of this interval. And then I could say else if roll is less than 6 out of 36, then I'm going to return 4. And I could say etc. Now, what's nice about that is it follows these mathematical rules, and the issue with it, or the other thing I'd say is that's nice about it, is that anytime we have a probabilistic distribution, so a collection of events, and the probabilities sum to 1, and you want to simulate this, if you know what the distribution of those events is and how likely each one is, you can use this same trick. So this applies, even though we're just summing 2 dice here, it can apply in a huge variety of different contexts where you just have a big collection of if and else if statements, or a match statement, or a dictionary, however it is you implement it. You generate a random number between 0 and 1. You assign the interval between 0 and 1 to a bunch of different subintervals where the width of the subinterval corresponds to the probability of the event that you care about. And then based off of whether which specific bucket, which interval this random number that you generated falls into, you assign it to that event. So that will always work. That's great. And it's very clear, concrete, repeatable, and mathematical. But what is it that we always want to remember? Anytime I use the word math, what is it that we need to really remember? Remy says lazy. Good. That's the critical answer is lazy. We have to be lazy, and lazy is the pathway to make more money. But laziness in and of itself, I think, is a virtue. And that's what we're going to apply here. So this is nice, it's pretty, it's mathematical, all that stuff. But I don't need to do anything this complex for this particular process. In this case, if I want to simulate the roll of 2 dice, all I have to do is roll a die once and roll a die again. So I've already simulated the roll of a single die. I can use the fact that I've done that to say, call the function once, call the function twice, and then return the sum of the 2 functions. Of course, there are other instances where we might need the math, but at least in this particular case, we simply trust the simulation, and you can build up more complicated simulations with simple simulations, which is what we're seeing here. What's nice about this too is that it generalizes. So imagine that I had said we want to simulate rolling 10 dice, and then you have to go and compute by hand all of the probabilities of all the different outcomes if we're looking at what's the sum of these 10 dice going to be. And that, to me, seems like it's probably going to be a nightmare. But in the case of implementing this as a simulation, we would just need to call the roll die function 10 times and then sum the result. So what I'm going to do here is to not sum 2 dice. I'm going to sum a collection of dice where I'm going to take this as a parameter, and I'm going to call this numDice as an integer. So let's say numDice is our integer, and then it's going to return an integer based off of rolling or simulating the result of numDice dice and then returning their sum. And now we are in the realm of all we have to do is call this subroutine, and all we have to do is remember how I want to do something n times, which is at this point probably pretty comfortable. We get to use our old friend the for loop. So we're going to say we set the total equal to 0. What's nice about this sort of function too is, especially if you've made it through some of the challenging things that we've seen, especially towards the end of our initial chapters, now we sort of have a chance to take a deep breath, go back, and start feeling comfortable about a function like this where I say it should hopefully start feeling like second nature if you're new to this, because I'm establishing a total equal to 0. I'm eventually going to return that. And then in the meantime, I want to range over the number of dice and add one roll's value to the total. So in this particular case, I'm still not interested in the index that we're working with here. It's never going to apply. We're just going to range over the number of dice, and at every point in time, I'm going to call roll die. And what am I going to do with it? So I could say x equal to roll die, and then I could say total plus equal to x. Although at this point, I think we probably are comfortable enough to say, I can do that in one line. So I'll call the function as a subroutine, and whatever it returns is an integer between 1 and 6, and I'll add that into the total. Of course, what I probably should do, certainly test the function, but I probably should go into main, and then I can say let's call sum dice of 2 just to make sure that everything is working. Simulated sum of 2 dice. And I can run that, we get 10. I can run it a lot of times, and I'll continue to get different values. So now we can say, oh, I got a 12, nice. We can now simulate this process of rolling 2 dice. If for whatever reason we wanted to make this, I don't know, 200 dice, we could simulate that too, and it's still going to be quick. All right. Although when I do this for 200 dice, anybody notice anything? Especially when I go to 2,000 dice. What happens when I run this multiple times? No small numbers? Yeah, that's true. What else happens? Sums are pretty close. That's right, they're pretty close to each other. So any sort of volatility that you might have had with rolling 1 die or 2 dice, everything's starting to hone in on a value. So in this particular case, I don't think it's going to be very surprising that the average value here is 7,000. When you roll that many dice, you're going to get something that's not exactly always equal to 7,000, but pretty close. Yeah, so we're getting a law of large numbers here for sure. Okay, now we can roll dice, which is good. And what's good about that is it means we can simulate any game that involves dice. We're not far away from being able to do that. We should probably do it then as an example. And the game that we're going to simulate is the Queen of the Casino, which is called Craps. I don't know if it's called that. I don't think it is, but that's what I'm going to call it. All right. And I have, to build off what we've done, we're going to keep everything in this dice folder. So the functions we've written are going to be pretty useful. I probably should show the rules of craps, though. So if you may have played the game before, there are a lot of different ways of making bets on the game. But in its simplest form, you have a player rolling dice, and they roll the dice once. So you have 2 dice, you roll the dice once. And there's 2 possible outcomes, or 3 possible outcomes. First off, if you roll a 7 or 11, then you win, and you get your money back in addition to the amount of the wager. So if you wagered $100 on this, you get $100 plus $100 back, so you get $200 back. If you roll a 2, a 3, or a 12, then you're going to lose. So there's 2 circumstances where you either immediately win or you immediately lose, and then you can move on to the next run of the game. There's a third outcome, though, which is that, well, what happens if you roll a 4 or an 8 or one of these other numbers? And if that's the case, then you stand at the table and you keep rolling. So I'm going to call the value X. And as you keep rolling, the game is going to continue until one of 2 things happens. One, you could roll your number again, in which case you win. So if you rolled a 6 initially, you're wanting to roll another 6. However, if you ever roll a 7, at that point in time, you lose the game. So the 7 is a good thing. It's a lucky number when you start the game. But if you don't roll a 2, 3, 7, 11, or 12, then on your subsequent rolls, the 7 becomes a loser. 3, 12, 11, all other numbers are irrelevant. And so you're just trying to roll until such a time as you roll the first thing that you rolled, or, in which case you win, or you roll a 7, in which case you lose. So there are a lot of variants of this game and a lot of different ways of betting on it, but if you're betting with the person who's rolling the dice, this is the standard way to play the game. What we want to do is to say, well, we know that around the world, casinos have become very wealthy watching people lose their money. And one of the things that we might do is to say, if we know that over a huge number of trials, everything's probably going to about even out. Well, why don't we do this? Why don't we write a function that is going to figure out on average how much are you going to lose if you play this game? And that average amount that you lose, or the other way of looking at it is, the average amount of money that the casino is going to win over time as an average of over the number of trials that you've played. So it's the average amount won per game, and I should say also per unit of currency wagered. That is known as the house edge of any game. So the higher the house edge, the happier the house is for someone to stand there and play it. And we're going to call our function compute craps house edge. And what this needs to take is, I should say, determine the house edge of the dice game craps. So we're going to say parameters. Well, I need to know how many trials am I going to run this. So I'm going to have a number of trials as an integer. And then we're going to have a return. And the return that we're going to have is a float. And that float corresponds to the house edge averaged over num trials games, where we wager a single unit of currency each time. So I've said we now know that we need to have num trials, which is an integer, and we know that we're going to return a float. So we add our type hints as well. I suppose we probably should return an error if num trials is funky. So let me check that. And that's an easy check. So if I don't run it for any trials, that would be bad. So I'm going to raise a value error. I'll say error non-positive number of trials given. But we don't have to do extensive error checking because there's just this one parameter. And we know we're wagering $1 per game, or 1 unit of currency per game. So this gives us our first glimpse at what is called Monte Carlo simulation. Which is named after the famous casino in Monte Carlo. And how it works is to say, generate a large number of randomized trials to make an estimate of a simulation. Okay. And we'll apply this to the context of something else, which is simulating a presidential election, or we'll have a bunch of simulated randomized elections based on our polling data. But the same sort of thing applies in a huge, this paradigm applies in a huge collection of different human endeavors. So when you look at weather modeling, this is where weather models come from and why they've become more powerful over time, because, well, we have better models, but we're also able to run a greater number of trials. Now, the overarching idea here then is that we're going to simulate some process, and in this case, we're going to take an average of over all of those trials, what happens in the long run. And so I'm going to keep track of a variable called count. So this is the amount won if it's positive, or lost, in which case it's going to be negative. At the very end, so in keeping with what we often do in the course, of starting with whatever our most important variable is to keep track of what we care about, and then returning either it or something involving it at the end, we think about what is eventually going to be returned here. After I play this game like a million times, I'm going to have some amount that I've either won or I've lost, and I want to return that amount divided by the number of trials. Okay, so I called this count. I could call it amount. There's a lot of different things that I could call it. And then I think, well, I've got a lot to do here, right? And the natural way of looking at this, the first time you see something like this, is to think, I've got to get all the rules of the game, right, somehow encoded into this function. And I know there's a lot of possibilities. It can be intimidating to look at it first, because you think, well, I've got 3 different big possibilities, and then I'm going to have to keep rolling until I hit my number X, or until I roll a 7. And right, there's going to be a lot to do here. Except remember, the key word is always lazy. And so the question becomes how to do that. So how can I be as lazy as possible? I can be as lazy as possible by saying, well, I know I'm going to do this. I'm going to do for something a number of trials, total different occurrences. And then I want to play the game. So I want to play the game n times. On the highest imaginable level, if I'm simulating this, that's how I'm thinking about it. I'm simulating someone playing the game that many times. And then I say, well, if somebody plays the game, what is it that I actually care about? I just care about, did this simulation result in a win or a loss? And that's a binary outcome, right? So the only thing I have to do is to say, I'm going to set some outcome equal to the result of playing the game of craps just one time. And that function, I said, well, it only needs to return one of 2 things. So it's going to be true or false, corresponding to a win or a loss. Then we say, well, did we win? And here's where we can say, if so, and it's tempting to write if outcome equal to true, count plus equal to 1. You probably should start getting comfortable with the fact that you don't ever have to test if something is equal to true. So you can just say if outcome, because if it's true, well, you'll enter the if block. And if not, well, we lost. Okay, and so in that case, we're going to say count minus equal to 1. But we win in this one. All right, as they always, I think they used to say this in craps. I don't know if anybody said it in about 50 years, but they'd always say winner, winner, chicken dinner. So we'll keep that there. And then all of a sudden, magically, the function is complete. So the reason why, of course, is that we've delegated the work to our minion. our subroutine play craps once. But this is something we're going to see for really a while in the course, which is that a lot of times we want to do something n total times. If I want to simulate something or do something n total times, the most natural way of doing it is to just say, look, let's have a for loop that ranges over those n things, which in this case is the number of trials, and then just call a subroutine. So this type of thinking is going to be very helpful for us as we go through the course for the foreseeable future. In the meantime, let's write that subroutine. So now instead of me thinking about how complex this is going to be if I do it a million times, I just think I'm doing one thing a million times, and that one thing that I'm doing is called play craps once. And at the end of this, when I say, let's think through this, it's a doc string. I can even think about this function as a worker who's going to play craps once, and the worker doesn't need to know anything about what they're doing other than I'm playing craps once. So there's no number of trials or anything like that. So there's no parameter that's necessary. And then you say, what does this need to return? Here's where we say it needs to return a Boolean. True corresponds to a win, and false corresponds to a loss. And so I know then that the function is going to return a Boolean value. And I should say, on a high level, I know what this does. This simulates the process of playing craps one time for a single unit. Well, I guess it doesn't matter what the currency is. Returning true for a win and false otherwise. I don't have any error messages here because there's no parameters. Great. And here's where I get to play the game. So I need to think through what is it that I'm simulating in this particular case. And if I go back to my rules, in fact, I probably should just copy the rules down. So I've got them in front of me. And I'll make them a little prettier here. Okay, just separate them out a little bit. So I roll 2 dice, and that gives us a sum x. And then we're going to check the value of x. Fortunately, we've already written this function to sum 2 dice. In fact, we could do it for an arbitrary number of dice. So here's where I'm going to say the first roll, that's what I'm going to call x here, is equal to sum dice, and sum dice is just going to take the number of dice that we care about, which is 2. And that gives us our x. And then we can say, okay, did we win? What constitutes winning? We have this one first case where we know immediately if we've won or not. And that's based on if it's the case that first roll is equal to 7, or if first roll is equal to 11. If that's the case, it's an instant win. So what does the function need to do? The function just needs to return true. There's another case, which is where we lose immediately. And if we look at the rules, well, that's if the first roll is equal to 2, 3, or 12. So if it's the case that first roll is equal to 2, or it's equal to 3, or it's equal to 12, in either of those cases, we're going to return false. So those are the easy cases. So this is case 1, this is case 2, and then we have the more typical maybe case, which is we roll something else. So we keep rolling until we either roll the original number, which is going to be a win, or we roll 7, which is going to be a loss. And now here, my question for you is, what exactly is going to be our looping condition, right? So for how long are we going to keep doing something? What should we do? Until a 7 is certainly a possibility. But that's just one thing that could happen. Another good idea is, well, we could generate another roll. Yeah, so we could say new roll. I like this. And that's roll the dice. I guess it's some dice of 2. A lot of folks in the chat are saying this. I like this. And then we could say, while it's the case that new roll is not equal to 7, or new roll is not equal to first roll, and this is where we keep rolling. And yeah, we need a check here that new roll is 7 or 11. And so here's where we would say new roll is equal to some dice of 2, and we also need to check that new roll is 7 or 11. I should say check if. And that would mean we would say, yeah, right, we need to say if it's the case. I don't know why I keep saying 7 or 11. 7 or first roll. Okay. So I say, is it the case that new roll is equal to first roll, and that's a win? So we would return true. And if new roll is equal to 7, then we would return false, because we lost there. And then I would take this stuff, right, and I would copy it down, and that's all good. I'm just copying everything here, and we'd have a function that looks generally like this. Need to indent everything to the same level. All right. Now, I should feel a little icky. This isn't horrible, but I should feel a little icky about what I just did, right? What did I just do, and what have I told you we should be cognizant of doing when we're writing code? Good. I'm seeing we've got some good memories. Anytime I see the exact, lots of nesting, good. Lots of nesting I'm not a fan of. But in particular, copying and pasting code for a lot of reasons. I mean, for one, what happens if you realize something is wrong in one place? Now I've got to fix it in 2 places, right? And so, but also just from this perspective of there's a certain elegance about not having repeated code in a lot of different places in your file. So this sort of structure is okay, but I might write it the first time and say, I feel like I could do a little better than this. Like there must be a way of writing this function in a way that doesn't require this copied code, as well as in a way that almost might be reflected better in terms of the rules, in terms of if you think about like simulating a worker doing this, what it is that they're actually going to do. So the condition that I didn't hear, which is what I'm going to do, is practically speaking, when you're playing craps, you're going to keep rolling for as long as it takes. That's the simplest way of saying it, right? And there's a possibility that you might stand at the table until the end of time. But no one who plays craps is worried about that, right? So I think they have bigger fish to fry. But you might have to keep rolling like 100 times. And so you simply don't roll a 7. You don't roll your initial roll. And I think if you did this 100 times, you're not going to be worried to think, I'm never going to leave the casino. So the different way I'm going to write it is to do something that might seem very dangerous, but it's to say while true, and to acknowledge John has a great way of describing this, to say there is a vanishingly small chance of having an infinite loop. So this looks like an infinite loop, but it won't be with probability 1. Okay. And the reason why is that I'm going to have some positive probability every time through the loop of leaving the loop. And so over time, there's no way I'm going to never leave the loop because, well, eventually you're going to roll a 7 or you're going to roll that X. So in this particular case, I'm going to say our new roll is equal to some dice of 2. And is it the case that the new roll is equal to the first roll? Well, this is good. I won. And so I'm going to return true. Else if the new roll is equal to 7, now 7 is poison, and I lost. So I'm going to return false. And you're so tempted, I hope you're tempted, because it's been the way that we've written code for the whole class. You're so tempted to write something, like else something, right? And yet we don't need to do anything. We've got our 2 cases that I care about. The else is just keep rolling. And how do we represent keep rolling? Just start the loop over. So I don't need to do anything here. So if I roll the first thing that I rolled the first time, I win. If I roll a 7, I lost. Otherwise, I just carry on. And when we hit the while loop again, true is going to be true if you can believe it or not. And we're going to set new roll equal to some dice of 2 and carry on. Of course, we should probably play the game, right? So let's play the game. Let's go to main. And I'm going to set in main. Get up there. Yes, I've written a lot of code. In main, I'm going to say, first off, let's range 10 times. Let's set an outcome equal to the result of playing craps once. And I'm going to say if outcome is true, we're going to print we won. So we've simulated it once. Else, we print that we lost. And I mean, you could get fancy with this and actually print the collection of rolls each time, but I'm interested on a high level of just knowing did I win or lose. So I'll save this. And the reason why I only care about whether I won or lost is because I'm not so interested in seeing, right, like what were the actual sequences of dice rolls that I had. What I'm interested in doing is saying what happens in the very long term when everything averages out. And that's what I truly want to compute with Monte Carlo simulation. So when I save my code and I run it, we can see, okay, I lost 5 times, and then I lost 4 times, then I won 5 times, and then I lost a 5th time. So I'm even Steven. Anybody have a particularly good result or a particularly bad one? Maybe we just have some people who are terrified of casino games, and that's okay too. Claudia, also 5 out of 5. Ooh, won 1 time, lost 9 times. Not going anywhere with you. Whether it's a casino or otherwise. All right, there's a lot of winners. And what we're seeing is, well, I'll do this for a larger number of trials. What we really want to do is run this for a bunch of trials. So I want to set num trials equal to 1,000, say. And then what we can do is say the edge that I'm interested in is to say compute the craps house edge of craps for this certain number of trials. And then I'm going to print, and I'm going to say we'll have a fancy string, so an F string that says that the estimated house edge with num trials total trials is, and then what I want to print is, actually I'm not going to do it that way. I want to print the edge to 6 decimal places, and then close the string. And I can be a little more precise here by saying I want to have this in terms of percentage. So I'm going to say that's about edge times 100. So this will multiply it from a decimal number to a percentage. And I want to represent that to 3 figures and say percent of the amount wagered per bet. So this is getting normalized across. I could be wagering $100 each time I play it, or 10 cents each time I play it. I doubt you'll find a casino where they'll take a 10-cent bet, but regardless of how much I'm wagering, what I really care about is the percentage here of the amount wagered per bet that we're going to lose, or that the house is going to win every time we play. And now I can save it, and I want to run this. So before I run it though, and well, I'll run it first, and I'll show you what I get, which is, I did something bad. Dot 3, dot 3.3 colon 0.3f. Okay, let's try that again. All these are just tests of you. You think that these aren't intentional, or that I'm tired or something like that. It's not that. I'm just making sure that you're on your toes. So a lot of people said colon, good. So I needed a colon there. It's fine. And I'm losing about 0.4% actually. What I should say is, this is a little imprecise because I've represented the house edge. I should say this is the estimated average amount won. And because it's positive. So at the end of this process, what you're going to see is I ran it a few times. So let's ignore those. Let's ignore those times and say, here's what happened to me. So I ran it 1,000 times, and I get that I actually won, on average, 0.018, which is about 1.8% of the amount wagered per bet, which is good. And I could multiply this number by 1,000, and that's my total amount won or lost. Anybody do better than this? Anybody do notably bad? Got some more unlucky people. So if you see a positive number here, it means that's the average amount that you've won, which means the house lost. So the house edge would be, if I want to change this, I think about it as the negative. For every dollar you lose, the house wins. For every one you win, the house loses. Somebody's getting negatives every time. That's not good. If we think about what we should do, though, if I want an accurate measurement, what we could do is I could say, for every person who ever runs this, let me know for your 1,000 simulations. Let me know how you do. And then what can I do? I can just take the average of all those things. That sounds like a simple approach. It's getting at the two ideas. Number one, we need to run this for more simulations. So I need to up number of trials until it becomes an issue where it's going to take me longer than I care to know about waiting. The second point is that if we did that, so I'm going to say, everybody who ever runs this lets me know their result. And then what I will do is I'm going to average them together. That might seem simple, but that's actually something that we can implement on a computer. That's a big parallel algorithm. So we will do that very thing in a later chapter when we learn about parallel and distributed computing, where we can separate tasks over not multiple humans, but multiple machines, and then somehow consolidate everything that those machines return into one final conclusion. So we could have a parallel algorithm for simulating craps by just doing this over 100 computers and compiling the results. It turns out that the computer you're watching this on has multiple machines inside of it. And so when we transition towards parallel and distributed computing, I will show you how we can divide a task using code, using Python code, that will work by dividing the work over all of those different machines inside of the computer that you're seeing this on, which is pretty neat. It's especially neat because we can see this from the perspective of an introductory course, and we can do real applications for it. So we'll come back and do our crap simulator, where we see how would I do the crap simulator using the fact that my computer has 8 cores or 16 cores or multiple different machines in it, and I want to use the same idea, and then how can I do something more advanced than that would be scientific. So hang on to that thought. Hopefully you'll stick with us until we get to the parallel and distributed part of the course. For now, I don't need something that fancy. I just want to run this for a larger number of trials. And now when I run it for, let's say I could run it for 1 million trials, I have to wait for a little bit of time. And now notice I have a negative number here, so the house is winning. And so one of the things I could do is to say the estimated house edge is to then take the negative of the edge, because when I run this now, it's about this number. So it's represented as a positive because this is from the house's perspective. If we lose money, the house gains. And I'll do the same thing here to say negative edge times 100. And we'll see that that's about 1.3% of the amount wagered per bet. And now what can you tell me? Is there anybody who, when they run it for 1 million trials, anybody out there who won? So does anybody have a negative house edge? If so, let me know. I'll be very impressed. Does anybody have a number that's not between 1.3% and 1.6%? And if so, what is that? If not, what is this reminding us of? In the meantime, what I'm going to do is say it. Why don't I just add a 0 here and wait on it and see what happens? So our code is finished, and it's saying that the house edge here is about 1.395% of the amount wagered per bet, and I could run it again and see what happens. So it'll take me a few seconds here. AB is saying from his old gambling course, the house edge on a simple bet like this is 1.4%. And that's good. I'm intrigued by this notion of a gambling course. Maybe I should turn this into a gambling course. The funny thing about that is, even though we're going to transition towards election simulation here, we'll wind up talking about gambling again. It might not seem like that's the most connected thing, but it's about as inherently connected to gambling as you can get. Hang on to that thought, though. We're going to get there soon. So everybody that's running this is probably getting something that now is even in a tighter window, which is to say that the house is going to win about 1.4% of the amount wagered on average per bet. So if you make a bunch of $100 wagers, on average, the casino is going to win about $1.40 every bet. And this might not seem like very much, but when you compound it over everyone who wagers on craps around the world and factor that over an entire year, you start to see why the casinos are so nice and why they say the house is always going to win. All right. We can play a game, right? Big deal. Good. Great. One of the things I would say is you may not have any personal affinity to craps, but I want to take a look at what is it that when we look at our function, so we have some dice, we have this function called compute craps house edge for a number of trials. And I want you to notice, what is it about this function that's specific to craps? And there really is nothing. So the only thing that's special about craps here is we called this function play craps once. But you could imagine I want to simulate any game with an outcome that's win or loss. And in this particular case, I also need to assume, I guess, that I either win back my money plus an additional unit of currency, or I lose my bet. So everything here is simulated as even odds. And I could change that a little bit too. But the idea is anytime you have any sort of game where you either win your money back plus the same, or you lose it, that sort of binary game with reasonably simple odds could get simulated just by changing this function. So you can imagine we could simulate some other game that we're interested in. And I would say, let us know this. If there's some game that you're particularly interested in simulating, do the same sort of thing and substitute out play craps once with play the game that you're particularly interested in, or do something with slightly more exotic odds and find a way of implementing that as well. But this framework is going to extend to a huge variety of different simulations. We're going to see next time that we could simulate this for something that's not a game, but is essentially similar, which is to simulate a presidential election in the US from state level polling data and see how that changes over time and see how there are pitfalls inherent in that process as well. But we'll save that for next time. So we'll wrap up what we do with building an entire election simulator next time. That's inspired by everything that we've done here with the foundations of Monte Carlo simulation. And that's it for now. So until I see you next, like, subscribe, connect with us with all the ways we have in our description. And of course, as always, happy coding.